Reverse thrust is a critical component in the arsenal of technologies that ensure the safety and efficiency of modern air travel. While most passengers are familiar with the roar of engines propelling a plane into the sky, fewer are aware of the technology that safely slows the aircraft upon landing. Reverse thrust, also known as thrust reversal, plays a pivotal role in reducing wear on the aircraft's brakes and improving the stopping capability on shorter runways. Its significance becomes particularly evident in adverse weather conditions, where stopping distances can greatly increase. The concept behind reverse thrust is relatively straightforward. It involves redirecting the thrust of an aircraft's engine so that it opposes the forward motion, thus helping to rapidly decelerate the aircraft upon touchdown. Despite its simplicity, the engineering behind this system is intricate and tailored to different types of aircraft. Whether it's a jet or a propeller-driven plane, the mechanisms and operational procedures of reverse thrust vary significantly. Reverse thrust is not only about enhancing safety, it also contributes to the longevity of the aircraft's mechanical systems. By alleviating the burden on the conventional braking systems, reverse thrust helps in reducing maintenance costs and prolonging the operational life of key components. This introduction of reverse thrust has been a game changer in aviation, allowing planes to operate more safely and efficiently in diverse conditions. Engaging with this topic offers an intriguing glimpse into the intersection of physics, engineering, and safety in aviation, a symphony of elements working together to bring giants of the sky to a safe halt. Jet aircraft employ reverse thrust mechanisms that are both fascinating and complex. At the core of this system are the thrust reversers, devices integrated into the engine structure. Upon landing, pilots activate these reversers, causing blocker doors to redirect the high-speed exhaust gases forward against the direction of travel. This action creates a powerful counterforce that dramatically reduces the aircraft's forward momentum. There are primarily two types of thrust reversers used in jet aircraft, the clamshell and the cascade type. The clamshell type works by employing doors that pivot open to block the rearward expulsion of exhaust, redirecting it forward. In contrast, the cascade type utilizes a series of vanes to redirect the airflow from the engine's fan outward and forward around the sides of the engine. Each type has its own specific advantages and is chosen based on factors such as the design of the aircraft and its operational requirements. The activation of reverse thrust is a critical phase during landing. Pilots must judiciously use this feature, as deploying it at the wrong time or in incorrect conditions can lead to complications. Typically, reverse thrust is engaged only once the aircraft has touched down and is moving along the runway. This protocol ensures that the aircraft remains stable and that the redirection of exhaust does not affect the structural integrity of the engine or the safety of the flight. Understanding the mechanics of jet aircraft reverse thrust is not merely an academic exercise, it's a crucial aspect of pilot training and aircraft design. It reflects an intricate balance between mechanical innovation and practical application in aviation safety protocols. This balance ensures that air travel remains one of the safest modes of transport in the world. Propeller-driven aircraft, while operating on different principles from their jet counterparts, also utilize reverse thrust to enhance their stopping power. In these aircraft, reverse thrust is achieved by changing the angle of the propeller blades. This adjustment makes the blades push air forward rather than pulling it, creating a decelerative force that helps slow the aircraft after landing. The mechanism responsible for altering the blade angle is known as the propeller pitch control. By moving into a negative pitch or beta range, the propeller blades effectively reverse their thrust. This capability is not only useful during landings, but can also be employed in flight to reduce speed or during taxi operations to maneuver around the airport. However, the use of reverse thrust in propeller-driven aircraft comes with its own set of challenges and considerations. For instance, the sudden reversal of airflow can create turbulent conditions that may affect the aircraft's control surfaces. Pilots must be trained extensively to handle these dynamics, ensuring that the deployment of reverse thrust does not lead to loss of control or undue stress on the aircraft's structure. The design and maintenance of these systems are critical. Regular checks and balances are essential to ensure that the propeller pitch control functions flawlessly. This attention to detail in the operation and upkeep of reverse thrust systems is a testament to the aviation industry's commitment to safety and reliability. These systems not only enhance operational efficiency, but also bolster the confidence of both crew and passengers in the safety of air travel. Implementing reverse thrust during landings involves a delicate balance of factors that pilots must navigate. One of the primary operational considerations is the speed at which reverse thrust can be safely and effectively engaged. For jet aircraft, reverse thrust is most effective at higher speeds, which is why it's typically deployed just after touchdown. However, the effectiveness diminishes as the aircraft slows, making it less useful at lower speeds. This characteristic necessitates precise timing and control from the pilot to maximize the decelerative force without compromising safety. Noise is another significant factor when it comes to the use of reverse thrust. In many urban airports, noise abatement procedures limit the use of reverse thrust to certain times of the day, or require that it only be used minimally to reduce the impact on nearby communities. These restrictions pose additional challenges for pilots who must achieve safe stopping distances without the full use of this decelerative mechanism. Environmental conditions also play a crucial role in the operation of reverse thrust. Wet or icy runways can affect the traction of the aircraft's tires, making it harder to slow down. In these cases, reverse thrust can provide a critical supplement to the brakes, helping to prevent runway overruns. However, pilots must also be wary of potential hazards such as water ingestion by jet engines, which can occur if large quantities of surface water are present. Furthermore, the maintenance and readiness of reverse thrust systems are paramount. Failures in these systems can lead to increased stopping distances and potential safety risks during landing. Regular maintenance checks are required to ensure that all components of the reverse thrust system, such as actuators and control surfaces, are operational and that no mechanical issues are present. These operational considerations underscore the complexity and importance of reverse thrust in ensuring the safe and efficient operation of aircraft in varying conditions. Safety is paramount when it comes to the operation of any aircraft system, and reverse thrust is no exception. Pilots receive extensive training on the correct use of reverse thrust, including simulator sessions that replicate various landing scenarios. This training ensures that pilots are prepared to handle the system under different runway conditions and can make informed decisions about when and how to deploy reverse thrust effectively. Aircraft manufacturers and maintenance crews also play a crucial role in ensuring the safety of reverse thrust systems. Regular inspections and tests are conducted to check the integrity and functionality of thrust reverser mechanisms. Any anomalies found during these inspections are addressed promptly to prevent malfunctions that could affect safety during landing. Operational protocols are also in place to guide the use of reverse thrust. For example, guidelines specify the minimum altitude and speed at which reverse thrust can be engaged to avoid situations where its use could lead to instability or control issues. These protocols are continuously reviewed and updated based on the latest safety data and technological advancements. The collaboration between pilots, engineers, and aviation safety experts is vital in maintaining the high safety standards associated with reverse thrust. Through continuous training, rigorous maintenance, and adherence to strict operational protocols, the aviation industry strives to harness the benefits of reverse thrust while minimizing the risks associated with its use. This comprehensive approach to safety ensures that passengers and crew can rely on reverse thrust as a critical safety feature during landings. The introduction of reverse thrust has had a profound impact on modern aviation, significantly enhancing both safety and efficiency. By reducing the reliance on traditional braking systems, reverse thrust has enabled aircraft to land safely on shorter runways, a factor that has facilitated the expansion of air travel to airports with limited infrastructure. This capability is particularly crucial in congested urban areas where space constraints limit runway length. Moreover, reverse thrust contributes to the reduction of wear and tear on the aircraft's brakes and tyres, leading to lower maintenance costs and longer operational lifespans for these components. This economic benefit is essential for airlines operating within the competitive aviation market, where cost efficiency is as crucial as safety. The environmental impact of reverse thrust is also noteworthy. By enabling quicker deceleration, reverse thrust reduces the time aircraft spend on the runway, thereby decreasing fuel consumption and associated emissions during the landing phase. This contribution is in line with the aviation industry's ongoing efforts to minimize its environmental footprint and promote sustainable practices. As aviation technology continues to evolve, the role of reverse thrust remains indispensable. Its integration into modern aircraft design underscores the industry's commitment to innovation that enhances safety, efficiency, and sustainability. The continued refinement and optimization of reverse thrust systems will undoubtedly play a key role in shaping the future of air travel, ensuring that it remains one of the safest and most efficient modes of transportation in the world.